Okay, so if I'm trying to look at Newton's first law and trying to remember, and I don't have a good memory like you, then I kind of look at this bit here, the first, and then I know that it starts with an I, and then I kind of remember, oh, Newton's first is the inertia law. So that's how I remember it. And so the law of inertia states that an object will remain at rest, right? There's obviously different definitions, but this is kind of however meant. So an object will remain at rest, right? Inert. Or continue in its will continue in motion, let's say, unless acted on by we're going to say resultant force. Or we could also say a net force.
Yeah.
Okay, so this is not so easy to understand if intuitively, unless of course we understand friction, because we think of say a tennis ball, and if we were to hit a tennis ball, eventually it kind of comes to a stop, right, on Earth. So it's going, and then it slows down, and then it comes to rest. But of course, we know why it's coming to rest, and that's because there is a net force acting on the tennis ball after you've hit it, or a cricket ball or anything, and that is that there's friction. So there's air friction and friction with the ground if it's rolling along the ground. And so friction is the kind of the net force, right? So friction would be your net force. So but if you didn't know about friction, this law, you'd go, well, hang on, an object doesn't stay at rest on the Earth, but if we think of it in terms of space, then it's much easier to understand, because there's no friction in space. And so if you were a planet or an asteroid, they kind of keep moving in their direction of motion. If they're going around a planet, well, then they're revolving around a planet because of the gravitational force of that planet. So, but it applies to everything in our known universe. Is this idea of inertia, that you need a force in order to change an object's current state. So that would be a definition, 2 marks. But then we kind of look and say, okay, so what equations are we looking at in this first law that they examine? And the main one I would say would be the F net equation. So F net. So F net is equal to the sum of the forces. So we did vectors, and so we have the sum of the forces. So let's think about something. Let's say we throw a ball up into the air, a cricket ball. Now, when we throw it down up into the air, at the point of release, there's a force from our thing, right? So at the point of release, we could say that, you know, you are applying a force, F. But then we have gravity pushing down, but the force that the applied force is big enough. You see it's larger. So we see our F net is kind of upwards. If we were to add these forces, let's say that the FG, let's say the ball was we'll take gravity as 10 and not 9.8 to make the maths easier. And the ball will say 100 grams, and it would be 0.1 kilograms times 10. And so you'd have a 1 Newton force going upwards, downwards because of gravity. So let's make this 0.1 kilograms. And then our gravity is 10 meters per second squared, the acceleration. And so the FG would be 1 Newton. But you could apply a force upwards of, say, 4 Newtons, and we have a net force of 1. So this is sort of inertia coming into play, because the cricket ball was at rest, and then you threw it up. But then we look at the scenario after you've released the ball, and it's now coming down, because the applied force is no longer there. And so your net force is down. So this is kind of a simplistic look, but when we think of Newton's first law, there's obviously a lot more at play. So because obviously the exams are not, the questions are not that simple, but the idea is that we want to get our force diagram right. So a free body diagram, right? Free body. So there's a force diagram and a free body. Do you know the difference between each?
I'm trying to remember now. It's
so free body is the dot.
Yeah, free body is the dot, and then the force diagram is or a box, whatever. It's same.
Yeah, and so they're exactly the same concept, but just the free body is kind of what physicists use. It takes the art out of it and having to draw these things, and just says, let's break it down to the forces. And the free body diagram acts that the point is at the center of gravity. We're going to leave the force diagram. The force diagram often will actually be given to you in the question. Force diagram. Well, not exactly, but it'll be. Sometimes they'll draw something with a block. You know, they'll draw a block thing. So we can turn that into a free body diagram, and so we did the basic one in the first bit. This is almost a free body. Just make this into a dot here. And this would be a simple free body diagram of an object in the air. Now let's do the basic one where an object is on a surface. And so an object on the surface of on the earth, let's say this is you. You would have your, we always have our gravity, G acting down, and that's whatever the object's mass is, times the acceleration, right? Because a force is F is equal to ma, right? So let's say it's just your mass times acceleration. And we're going to say 9.8 on Earth. And then we have the normal force that balances it out. And that's why there is no it's at rest. This bit here is part of Newton's second law. So we're going to go on to that pretty soon. I just want to, so that this would be the segue to Newton's second, but as long as you get the angles right on this. So if this is a 30-degree angle, you need to say that the gravity does act down, right? The gravity does act down. So I could put my gravity in purple here. But the big thing is to know that this gravity is broken up into two components.
FG parallel and FG perpendicular.
Yes, yes. So some of it is pushing into the slope, right? And so I'm actually going to do a dot because it's part of the same force. So it's you can draw gravity in purple and not the dotted lines in your actual when they ask you for the free body diagram. It's just when you do your calculations, you need to know that you have these forces, these two forces. So this would be F perpendicular. And then going into the slope is your F parallel. Sorry, perpendicular is going into the slope and parallel is going down the slope. And so your normal force acts in, it doesn't act upwards, right? It acts perpendicular to the slope. And so your Fn is actually going to be here. So this would be your Fn, your normal force is now acting perpendicular. So the force going into the slope is balanced by the normal force. And so it's those two forces cancel each other out. And so the only force that we're worried about in terms of moving the object would be the parallel force. But of course, this isn't necessarily a frictionless object. And so you could have a force of friction over there. And so this might be if it's not a frictionless slope, then this would be FFR. And you could also have an object, someone pulling the object in this direction. Let's do a different color. And if you get this force diagram right, then you are fine. That it should be easy. Not easy, but you can then just sum these forces. So it's key to get these things. So we could then do an applied force up the slope. Now, what gets even more tricky is that you could have the guy standing on the slope. So I'm going to change that. And he could be pulling it at an angle. And so this is the trickiest question that they kind of look at, is they put you on a slope and they also have the person doing an applied force. And so his can then be broken up into, part of it is actually almost lifting the object up, right? And then part of it is going along the slope. Does that make sense?
X and Fy.
Yeah. And so now you've got another one. So when you look at that, this one, let's do it in a different color. This one in pink here, that one actually makes the normal force smaller, because it's almost like it's lifting the object up a little bit off the ground. And so your normal force, that you actually against gravity. So your normal force doesn't have to be as big. So as long as you get that right, then you could say, well, if my applied force is like, say, let's put it in green, then I just have to make sure when I do my calculations, so let's say that this is a 40-degree angle here, that I break this up into that one that I drew in pink. And so do you see that if G hasn't changed, this blue, light blue one, but yet I've got a pink one pulling it up a little bit. And so my normal force will be not as big, because it doesn't have to be as large to counteract gravity. And then also I have, let's do another dotted line color. What do we not have? Let's do light green. And then we have this one going along. And so this green one then also has an applied force pulling it up. And so you have quite a lot going on in your force diagram, but the ones that you would have to write in your force diagram would be 1, then pink, 2, not the ones and dots, 3, and then 4. But then when you do your calculations, you just remember you need to break up the green one and the purple one. So that is kind of how it gets tricky. I just want to give you one tip, because a lot of people get confused with the sines and the causes. So what we do is we'll just do the gravity one. So what they'll do is they'll say FG sine theta, and then FG cos theta. Okay. Now I've picked this one because let's say that the force, well, let's give it a thing. So let's say the FG is just, we'll say that it comes to 50 newtons. So the sine theta would be 25 newtons, right? Because sine 30 is a half, but you put that on your calculator. Now, what do you get when you put in 50 cos 30 on your calculator? What do you get? Put your calculator with you. You got your calculator there?
Yeah. It becomes 43.301.
43.3 newtons. Okay, so this is what I do. So what you're looking at, I'm just going to hold this up, and then I'm going to hold it at an angle of about 30 degrees. And what can I? Okay, I'm just going to use. Do I have a block? Okay, we'll use this in here. So I'm holding it at 30 degrees. And so if I'm holding it at 30, I'm just imagining that is quite an acute angle, which means that most of the force is acting, you can see, so, let's make it 10 degrees because it's quite a frictionless thing. So if it's at 10 degrees or 30 degrees, if this is quite if there's quite a high friction between, friction, coefficient of friction, I'll get into that now, between the object and the surface, it's not going to start sliding down. But as I tilt this, it starts to slide down because it's getting more and more steep. So I like to look at the extrema of this in order to go, well, which is the cos and which is the sine? So if I now look at this angle here and see, oh, it's 30 degrees, then I look and go, well, most of the force is pushing into the slope, right? If this was like this, and it was like 90 degrees, well, it's mostly sliding down. So I go, well, until it gets to 45 degrees, which is between 0 and 90. So at 45, the force going down and the force going in is the same. But until then, 30 degrees means most of the force is going into the slope. And so I know that because it's an acute angle, this is then the one into the slope. And this one is down the slope. I think I did. So this one would be F parallel because it's slightly smaller. And then this light blue one, sorry, I should have said, was in light blue, that's into the slope. So F perpendicular to the slope. And it's the same when you look at this 40-degree one, right? You're going to go, well, 40 degrees is smaller than 45. And so most of the force is going to be 40. Most of it is going to be, if we were to put it on a, like this, make it like that, on a flat thing, and we made this 40 degrees. Well, which is it, if you were to bring it down to say here, where there's no slope, well, you go, most of it is along, right? So the F parallel is bigger, right? and then the slope, the force going up is bigger. And if I was to do that, most of it is, I'm almost lifting the object completely when I look at if it's going in that direction. So I go, well, 40 degrees means that most of the force is actually pulling. So my pulling force, so then when I put in my force, sine theta and cos theta, I then just go, well, which one's bigger? And then I look at the angle and go, okay, that must be the pulling force. Because then you can just imagine that if there was no angle, it would just be pulling the block along. So a practical application for this, we'll go into now Newton's second law, but that's the first law, is that these objects don't change unless there's a force. And which brings us nicely onto Newton's second law. I'm going to pause this video or stop this video, and then we'll do Newton's second law and how it applies to matric.